We're switching gears. So this whole chapter is about rational functions and polynomials. We just did polys in 4.1 and 4.2, and now we're moving to rational functions, okay? Before we do that, though, we need to be able to divide and use long division, okay? And this is a technique that we're going to need when we do goal number 3, which is finding oblique asymptotes. Okay, so we have to be able to do a little review of this. I started off with just numbers. Do you guys remember how to do long? I mean, I know it's been like 2nd or 3rd grade since you learned it. All right. Are we able to remember how to do long division? You guys remember how to take 127 and divide by 5? Been that long? We can't remember how to do that? So we take a look at 5. We say, does 5 go into 1? No. We say, does 5 go into 10? And you would say, yes. And then we say, well, how many times does 5 go into 10? And you guys can use your microphones. Again, I am videoing this, but it's not, you're not seeing your faces or anything. Twice. So I put a 2 up here. Okay. I multiply, right? 2 times 5 is 10. And now I subtract. Now what I say is draw your line, change your sign. Or subtracting. Draw your line, change your sign. 12 minus 10 we know is 2. And then bring down your remainder. That's 27. And then we do it again. How many times does 5 go into 27? And you guys would say 5 times. And 5 times 5 is 25. Draw my line, change my sign, I subtract, and now I get 2. Okay? You guys remember what we called this guy when there's nothing else to bring down? That's our what? Remainder. That's our remainder. Okay. If you want to write it like this, 2/5, you can. Okay. To be honest, we don't even care about our remainder. We'll only care about what we get on top. We don't care about what's left. And I'll explain that as we get into goal number 3, which will be really tomorrow. We're not going to finish these notes, so we'll finish them tomorrow. So when I take a look at number 2, now I have a binomial and I'm dividing that into a trinomial. Okay, so we do the exact same thing, but we look at just x. So I say, what up here times x will give me x squared, or what's x squared divided by x? And what would you guys say? What's x squared divided by x, or what times x gives me x squared? What do you think? Joe, Morgan, Lisa, Gavin, what do you guys think? Zach, Jess, Caitlin, McKelvey. What times x gives me x squared, or what's x squared divided by x? There you go. Now, just like we had 2 up here, we took 2 times 5 is 10. We take x times both terms, x plus 2. So x times x is x squared. X times 2 is 2x. I draw my line, change my signs. Positives go to negatives, negatives go to positives. These guys should cancel. And now I have 7x minus 2x is 5x. Bring it down. Okay. Now, when we take the quiz and test coming up next week, you know, sound effects, guys, need to be turned off, or make sure your mic is off, because if not, when everybody starts bringing the remainder down, they go, we're going to get, and we just don't want that. That'd be crazy. So turn those mics off. Does anybody know what movie that's from? That sound? It's from the 90s. 1990s. Mom and dad probably watch this movie every once in a while. Starts with a W. Anybody remember what movie that is? Anybody seen that movie from Saturday Night Live? Way before your time. Nobody. Have you heard of?
Is it Wayne's World?
It is Wayne's World. Yes. Wayne's World party time. Excellent. Oh man. All right. So make sure your mics are off. A little random fun fact. All right, we do it again. So what times x will give me 5x? And y'all would say positive 5. And now we got to take that 5 times x is 5x. 5 times 2 is 10. Draw my line, change both signs. Positives go to negatives, negatives go to positives. This guy cancels, this guy cancels. Boom, remainder 0. Okay? Now, one thing is, this is called the remainder theorem. Anytime you get 0 as your remainder, that means this is a factor of your trinomial. And that makes sense. If I have x squared plus 7x plus 10, that factors nicely to x plus 2 and x plus 5. Okay? Don't need to know that, but it's just a fun fact. All right, last but not least, sometimes you might see them like this. And this is what we're going to see later, is we want to look at this guy and use long division. Well, x plus 1 goes out in front, and then 2x squared minus 2x minus 1 goes here. Okay. If you ever had a missing term, like maybe you had just 2x squared minus 1, we would put in a 0x there. So if you're missing a term, replace with a 0. Okay. All right, we do the process. We say, what times x gives me 2x squared? And y'all would say 2x. So 2x times x is 2x squared. And then 2x times 1 is a positive 2x. Draw my line, change my signs. These cancel. And now I get negative 2x minus 2x. Now I'm at negative 4x. Bring it down. One more time. What times x gives me negative 4x? Or what's negative 4x divided by x? What do you guys get there? What times x gives me negative 4x? Or what's negative 4x divided by x? Use your microphone, use your chat. The faster you answer, the faster we move on. Try to get out of here early today. Question is, what times x gives me negative 4x? Maybe I froze there. There you go. Fantastic. Negative 4 times x is negative 4x. Negative 4 times 1 is negative 4. Draw my line, change my signs. Positives goes negatives. These negatives are now positive. Cancel. Negative 1 plus 4 is 3. Okay, that's my remainder. Actually, we're not really going to care about the remainder. We're only going to be looking up here. And that's what our oblique asymptote will be. Okay, so that is a little preview of goal number 3. This is a technique that we got to know how to do. Okay, we've done this in algebra. We did it in algebra 2. This is the 3rd time you've seen this. So it's a little refresher on long division. It's like 2 steps and done. All right, so goal number 0, done. Goal number 0 is done. There's Paige. She's got her Wi-Fi working here. All right. So here we go. If you're just joining us, we are working our way through chapter 4 notes. We have just done long division. We won't need long division until tomorrow, so I'll refresh your memory tomorrow. All right, ladies and gentlemen, this is a rational function. Rational, if I cover up the NAL, is ratio. So if I have a ratio, that's a fraction. Basically, we have a polynomial divided by another polynomial. Q of x can't be 0, though, because if that's 0, then that would be undefined. It would be no solution. So that's our domain. We've seen domain in the past. Okay, the domain consists of all real numbers except those in which makes the denominator 0. Okay, so on examples 1, 2, and 3, I'm going to highlight my denominators. Okay, and those guys cannot be 0. That's our domain. We want to find out what are our restrictions, what x cannot be. So I'm going to set each one of these denominators not equal to 0. because they can't be equal to 0. Okay. And we're going to solve. First one, find the zeros of this poly, x squared plus 8x plus 12. To do that, we find our factors. Teach me how to factor. Teach me how to factor. Everybody factor. Everybody factor. Show you what when you factor. All right, what are factors of 12 that add up to 8? Shout it out. What you got? What you got? Factors of 12 that add up to 8. 6 and 2. Fantastic. So I'm going to factor this to x plus 6 and x plus 2. Multiplied together is 12. Added together is 8. So that works out perfect. And then zeros is the opposites in these parentheses. We've seen this before. So x cannot be negative 6 and it cannot be negative 2. Okay. So my domain can be anything except for those. And the fancy way to write that is D equals the set of all real numbers such that x cannot be negative 6 and negative 2. Just like that. And then we're done. It can be anything it wants. You can plug in any number, but if I plug in negative 6, or if I plug in negative 2, on the bottom, it's going to make it 0, and 0 in your denominator is undefined. Okay? So when I look at number 2, I could solve this by factoring, or some people like the square root method. So I'll give you a reminder what that looks like. I would add the 16 over. I would get x squared cannot be 16, and then I square root. And what would you guys say is the square root of 16? Square root of 16 is how much, y'all? 4. But Mr. Gotch always says, don't forget the plus or minus. So if you want to do the fancy domain is the set of all real numbers, such that x cannot be plus or minus 4. A lot of people forget this. So maybe highlight it. Don't forget plus or minus. Okay. So I'm going to highlight that. I'm a highlighting kind of guy. I like to highlight those things so I don't forget it. Because again, you guys, during Rona time, can use your notes on quizzes and tests. You got it highlighted. It's going to get your eyes right there. Okay, so you don't forget. All right. So again, another reason is why it's plus or minus. I could factor this to x plus 4 and x minus 4. There would be 2 solutions. So if you're using the square root method, there should be 2 solutions. So don't forget the plus or minus. Last but not least, I've got x over x squared plus 9. Set that denominator equal to 0. As I solve, I would subtract 9. And what happens when you square root negative 9? What do you guys get? What's the square root of any negative? You guys know? Square root of any negative number. What happens when you plug it in your calculator? What's the square root of negative 9? Undefined. You get no real solution. It's imaginary. It's I. It's really plus or minus 3i. So there is no value that I can find that's going to make this bottom 0. Some people say, well, doesn't that factor x plus 3 and x minus 3? I'd say yes if that's negative 9, but it's plus 9. You can't find factors of a plus 9 that add up to 0. So that means my domain can be anything, all real numbers. Okay, so all real numbers is the domain. I can do anything I want. Okay, you can do the fancy R if you want all real numbers like that, or you can do the negative infinity to infinity. Okay, so your domain is all real numbers. There is no restriction in this guy's domain. So those are the 3 different types you guys will see. Okay, how we doing, y'all? We're okay. Again, we're not going to get through all these notes. This is going to be a 2-day set of notes, especially with shortened periods here. All right, 1, 2, and 3. Any questions? Give me a thumb. Where are we at with this stuff? Give me a thumb. I got 2 thumbs. I need more thumbs. 3 thumbs. Give me some thumbs. I got 4. I got 5. I got 6. I got a double thumbs up. Watch out, girl. All right, all right. And then people that don't have their cameras on, I hope you're paying attention, y'all. All right, guys, I'm looking at the second page now. Okay, just walk us through what a vertical, horizontal, and oblique asymptote looks like. Okay. So, vertical, horizontal, oblique, this one is a horizontal asymptote. Now, be very careful to make sure you say the whole word asymptote. If you don't, you will get in trouble by mom and dad and think you're swearing or something. We don't want that. So this is, again, a horizontal asymptote. Okay. So as x approaches infinity and negative infinity, your graph is going to start approaching a certain horizontal line. Okay. And that will never touch or cross that horizontal line. It'll just get closer and closer and closer, but never touch it or cross it for large values of x. Okay, so you might get a line like this, y equals 5. Okay, you remember it's horizontal. We've talked about in the past u, v, w, x, y, and z. If it's horizontal, it's a y equals. Okay, versus a vertical asymptote. If you have a vertical asymptote, it says on your graph, if x approaches some vertical number c, then for values of y or r of x is approaching infinity or negative infinity. So the line x equals c is a vertical asymptote. So basically, as you're getting closer and closer to a certain value for x, your graph is going to go up and up and up and up and never stop on both sides. Or it could go up to positive infinity and down to negative infinity on the other side. Okay, these would be examples of vertical asymptotes. Remember, vertical is an x equals. Okay, so this is going to be x equals, I don't know, -7 or x equals 5 or something like that. Okay, now something that you guys should know. This is tied into your domain. Okay, vertical asymptotes and domain aren't always the same, but they're very similar. Okay, so that's something to know. Vertical asymptotes are tied in with the domain value. So we find, and we'll talk more about this tomorrow, we will find vertical asymptotes in the denominator. Okay, we'll talk more about it tomorrow. Last but not least is if an asymptote is neither horizontal nor oblique, which means it's at an angle, it's not up and down or side to side, so it's neither horizontal or vertical, then it's an oblique asymptote. Okay, now oblique asymptotes are in the form y equals mx plus b. So you might see something in this guy like y equals, I don't know, 2x minus 8. Just making those numbers up. Okay, so that's an example of an oblique asymptote. To find those, we'll use a long division, what we just practiced on the warm-up. So to find those, we'll do long division. I'll explain that tomorrow. Okay. The first thing we got to do is just basically look at a graph. Okay. So examples 4 and 5. This is similar to your homework 27 through 32. So if you're doing my math lab, look on the left side and it'll say 4.4 number 27. So look at this and that should help you visualize what's going on here. Okay. So they're asking us to find the vertical, horizontal, and or oblique asymptotes from a graph. So as I take a look at my graphs, the first thing I want to do is I want to find these dashed lines. I got 1, I got 2 dashed lines. Those are your asymptotes. Your graph is getting closer and closer to those and never going to touch it. I hope you can see the difference between a rational function graph now and what a polynomial function graph. Polynomial function, what we just studied on 4.1 and 4.2, is basically a roller coaster ride, okay? This is not a roller coaster. Roller coasters are continuous with no gaps, breaks, or holes. If you ask me to get on this roller coaster, you're crazy, right? If I get on this side of the roller coaster, I'm gonna die, right? If I get on this side of the roller coaster, I'm gonna die. There's no way I'm jumping on this roller coaster ride, okay? Again, we got big breaks and gaps in my graph. So, we need to find any horizontal, and we need to find any oblique, okay? Well, these are vertical ones right here. And I can count my tick marks. This is over 1, 2, -3. So this one is right in the middle at -2. That's x equals -2. And this one is from the origin 1, 2, 3. So that's at +2. So I've got x equals ±2 are my vertical asymptotes. Okay. Now the one that's hard to see is this one. You can see my graph is getting closer and closer to the x-axis from here for large values of x's, and large value of x's this way. So it's hard to see, but there is a horizontal one going across. Now the reason why it's hard to see, number one, is you can't see a dashed line on top of a solid line. Okay, you just can't see it. Okay. So there is a dashed line, you just can't see it, and that is at the x-axis, which is y equals 0. So there is a horizontal one. For large values of x's, I can see my graph is getting closer and closer to the x-axis, never going to touch it. Okay. Oblique, you will definitely see oblique like you see on this one. This is an oblique asymptote. You will see those dashed lines. And if you don't see any dashed lines for oblique, then there is none. All right, questions with example 4. I think I'm frozen again. Frozen. Do you guys have any questions with example 4? No questions. Nada, nothing. All right, example 5. Here we go. I got vert, horizontal, and oblique. So I got vertical, horizontal, and oblique. What do you guys see? So this is where you stop what you're doing, turn off Netflix. What do you guys see here? What asymptote do you guys see? Jen, Gavin, Ryan, Paige, McKelvey, Sydney L, Morgan, McKenna. What do you guys see? Amshel, AJ, Mary, Connor. What do you guys see? What type of asymptotes do you guys visualize here? You see in this graph? It's an oblique one. Yeah, we got an oblique one for sure. This guy right here is oblique. Huh? Do you guys see any other? I'll tell you, there's one more asymptote here. What else do you guys see? Do you see a vertical one or a horizontal one? Take a guess. There is definitely a vertical one. Good job, Joe and Sydney. Fantastic. So as I take a look, you can almost see the little dashes right there and right here. Okay. And my graphs on this side is going up and up and up, and this one's going down and down and down. It's getting closer and closer to this y-axis, but it's never going to touch. Okay, remember alphabetical UVWX. This is vertical, which is right next to x. This is an x equals line. This is x equals 0. So there's one right there. Okay. And then Joe said that there's an oblique one right here. Okay, remember oblique, if you're doing oblique, that's y equals mx plus b. So we need to pick out the m and the b. So who's got the m and the b? What's my slope? And what's my b? What's my y-intercept? What's m and b? And you guys can use your microphones. You can just shout it out. Jose, what do you guys see? Sydney, Hayden, John, Lisa, Caitlin, what do you guys see? What's my m and what's my b? What's my slope and my y-intercept? Shout it out. What do you guys see? What's my slope? What's my b?
Is the slope -2?
Close. It's definitely negative. Here's 2 points. This point right there and this point. So it's down 1, over 1. So it's close. It's -1. So that's good that you saw it's negative. It's definitely declining. Definitely decreasing there. What's my b? Where's it across the y-axis? What do you guys got for that? Where's it crossing the b, guys? Lisa, any ideas? Lorelei? 0. Hayden says 0, yeah. So the b value is right there at 0, 0. So this is y equals -x plus 0, which is just y equals -x. Okay? And then there is no horizontal asymptotes here. There's none. Okay? All right, let's finish up. I'm going to do examples 6 and 8 real quick before we get out of here. This, ladies and gentlemen, is what we call the inverse function. Okay, when we look at this guy's domain, the denominator, this guy's denominator is all reals except for 0. If I plug in 0, 1 divided by 0 is undefined. Okay, now that means for x equals 0, there's an asymptote. So there's an asymptote at x equals 0. And visually, your graph will never ever get to y equals 0. It's just impossible. So there's a horizontal asymptote at y equals 0. And we've actually seen this in the chapter 2.4 library of functions. We talked about the inverse function. Okay, this is the inverse function. Well, if I want to plot a couple points, I would plot points on either side of this vertical asymptote. I would plot points at 1 and -1. Just nice, easy integers to the right of 0 and to the left of 0. When I plug in 1, I get 1 over 1, which is 1. So I get 1, 1. Okay? Now what happens is your graph is going to get closer and closer to that asymptote, never touch it. And it's going to get closer and closer to this one and never touch it. It's going to stay in quadrant 1. And then we plug in -1, I get 1 over -1. And I get -1. So I get a point in the third quadrant. And their graph gets closer and closer to that asymptote and closer to this asymptote, and it never touches it. Okay. This graph is symmetric to the origin, and it's been a while. This is an odd function. Odd is origin, even would be to the y-axis. Okay. And let's do this one before we get out of here. Number 7. This is kind of like the inverse function where the domain is all reals except for 0. If I set x squared equal to 0, I will get undefined. So I'm going to have a vertical asymptote there at 0. And I'm going to have a horizontal asymptote there at y equals 0. Now, if I make a table and I plug in 1, 1 over 1 squared is 1. So I get that same point, 1, 1. It's going to get closer and closer over here. Closer and closer over here. It looks very similar to that one. But now when I plug in -1 on the bottom, -1 squared is 1, and 1 over 1 is +1. So that will be over here at -1, +1. It'll be in quadrant 2. So my graph is getting closer and closer, never going to touch. Okay, so this is just the very start of graphing 1 over x and 1 over x squared. This one is symmetric to the y-axis. This is what we call an even function. So it's been a while since we've seen even and odd. Okay.